You may have wondered, how do we grow the field of mathematics? How do we find something new? That process involves some observation, creativity, and most objectively, proof. We're going to look at our first proof technique that everyone needs to know today. Let's get started. Let's say that we're playing around with some numbers and we say something like this. If I take 4 squared, I get 16. And if I get 8 squared, I get 64. And 12 squared is 144. And what I notice is that every time I square an even number, I end up with an even number. And so I make an observation that anytime I square an even, I get an even. We can't say that this observation is true until we can write an argument that shows this for all cases. Because there may be some integer way out there past 100 trillion that's even, and when I square it, I get an odd integer. And so the basis of proof is to clarify in all circumstances when this is a true statement or not, and this is actually how we grow the field of mathematics. Now, before we get started with our proposition that an even integer squared is an even integer, so before we actually prove our proposition here that we think that an even integer squared is even, we actually need to know what kind of proof techniques are available to us. The first one is called direct proof, and the way direct proof works is that we just take definitions, basic logic, and other proved results just to verify that this is a true statement. And that's the technique we're going to look at today. So first we need a definition. In this case, we need to know what an even integer is. So I'll define an integer to be even, for example, 36, if I can write that as 2 times something. 36 is 2 times 18. If I can factor a 2 out, then that is an even integer, and I think that makes sense to us. Another way we could say this is if I divide by 2, I have no remainder. So that's how we'll define an even integer. An integer is even if it can be written as 2 times k, where k is just some integer. In a similar fashion, we can divide odd, because if I divide an odd integer by 2, I don't get a clean result. I have a plus 1 remainder. So we'll define odd as an odd integer n if it can be written as 2k plus 1, where k is an integer. In other words, when I divide by 2, I get a remainder of 1. Okay, so we're going to use that fact, the definition of an even integer, to prove our proposition here. And we're going to practice several of them. And this looks weird at first. If you haven't done this before, the language can be kind of funny. So just follow along the best you can. If you have questions, just let me know. So let's start with an even integer. So I'm going to say let n be an even integer. So we know then, by definition, n can be written as 2 times k, where k is an integer. If you haven't seen this notation before, this symbol means element of, and this double stroke z means the set of integers. This is very, very common, so we're just saying that k is an integer. Okay, so now all we've done is we've established that we have an even integer. We need to now square it. So n squared is going to be the same as 2k quantity squared. And then we'll just let our algebra take over here. That's the same as 4k squared. And I need to show that 4k squared is even. Well, I know intuitively it's even because there's a 4 times something in there. But I need to use the definition, which is only 2 times something. So I'm going to say, but 4k squared is 2 times 2k squared. And 2k squared is an integer. So I'm going to rename that integer j to show cleanly that n squared is 2 times an integer. So by definition, n squared is even. And then we'll draw this little box for the end of proof. So now we have proven this for any number, even the ones past 100 trillion squared, or however far you want to go in the integers. We have now proven this statement. This looks weird at first. It just takes some practice. Again, it's all definition based. We just did a little bit of algebra, but mostly we appealed to our definitions. If you don't know your definitions well, this is going to be very difficult. Let's try some more though, just to get more familiarity. Alright, so this proposition says if n, and that's a mistake, it should say if n is even, then n squared plus 4n plus 1 is odd. Now, actually, do I believe that to be true? So let's try it. Let's take an even integer, maybe 4. Then if I take 4 squared plus 4 times 4 plus 1, I get 16 plus 16. I know that's going to be even, plus 1 odd. Okay, so I believe this is a true statement. We need to prove it. Okay, so we're going to let n be even. Then by definition, n equals 2k, where k is some integer, right? Okay, so now what I need to do is take n squared plus 4n plus 1 and show that's odd. And we're going to use the definition of odd to do so. So I'll say, so n squared plus 4n plus 1 equals, just replacing n with the value of 2k, I get 2k squared plus 4 times 2k plus 1, which can give me 4k squared plus 8k plus 1. Now, is that an odd number? The only way I know if it's odd or not is if I can write it 2 times an integer plus 1. Can I do that here? Yes, I can, because I can take out a 2 out of my first two terms. And so I have 2 times 2k squared plus 4k, and then let's let the plus 1 stay on the outside of this factoring. And so that can be written as 2 times j plus 1, where j equals 2k squared plus 4k, which we know is an integer. Thus, by definition, we said that n squared plus 4n plus 1 is 2 times an integer plus 1. This n squared plus 4n plus 1 is, in fact, odd. I hope that makes sense. Now, a couple of points. Sometimes students get confused on, like, what does k mean? A k just represents some arbitrary integer. So for example, if I pick an explicit example like 6, then 6 is 2 times 3. The value of k in this example is 3. But if I'm trying to prove this in general terms for all integers, for all even integers, and so I can't say it's 2 times 3. That doesn't classify all integers. So I say 2 times k, k being the dummy variable that we find depending on what our value of n is. It will get more familiar with more experience. Okay, this time we say if n and m are both odd integers, then m squared plus n squared is odd. Now, it's always good practice to try to test this before we start proving. So let's try it. So let's say n is, let's get an odd integer. How about 3? And how about m being 5? So if I square n and I square m, and then I add those together, I actually don't get an odd integer. So I don't believe this proposition is true, actually. Okay, but we can modify it to get a true statement, or at least what I think is a true statement. I believe the case is that m squared plus n squared, if they're both odd, the sum will be even. I use this example because I want you to see that you have to actually convince yourself of it to be true before you actually try to prove something. I mentioned the observation early on. By observation, I don't believe this is a true statement, but we're going to modify it to something that we do believe to be true. And let's see if we can prove that. So we're going to let m and n be odd. So in this case, I have to define them both to be odd, which is 2 times an integer plus 1. Now, here's a very common mistake. So m is 2k plus 1, and n is 2k plus 1. I see this all the time with young proofwriters. But if I say m and n are both 2k plus 1, then I'm saying that m and n are the same thing. Remember, k represents some arbitrary integer dependent upon our values of n, or m in this case. So to avoid this issue where I use the same dummy variable to represent two different numbers, I'm going to say let's let m be 2k sub 1 plus 1 and n be 2k sub 2 plus 1, where k1 and k2 are both integers. Okay, now what I need to do is square them each, add it up, and see if that result is even or not. I hope it is, I believe it is, but let's see. So m squared, I'll go ahead and add m squared plus n squared. That's going to be 2k1 plus 1 squared plus 2k sub 2 plus 1 squared. We let our algebra take over. This is usually where students feel the most comfortable. So if I square the first one, I get 4k1 squared plus 4k1 plus 1. On the second side, I have a similar thing, 4k2 squared plus 4 sub k2 plus 1. Now, when I combine my like terms, I don't have a lot of, but notice that those plus 1s add up, I'll write it at the end here, to be a plus 2, which will allow me now to factor out a 2 out of everything. So I have 2 times 2k1 squared plus 2k1 plus 2k2 squared plus 2k2 plus 1. That is even, right? Even though it looks weird, it's 2 times an integer. So we'll say that's equal to 2 times j, where j equals that long expression that we don't really care about except that it is an integer. So thus, if m and n are both odd, m squared plus n squared is even. End of proof. Okay, this one was a little bit more involved, but not too bad. The issue was that we had 2 integers starting out, and so we have to make sure that we keep up with 2 different values of k. We also made sure to test our observation, not just blindly follow it. All right, let's try one more. Okay, this time it says we have any integer we want, then n squared plus n plus 8 is even. Let's test it. Let's make sure that we agree with this. Okay, so let's pick anything we want. How about 1? So then I have 1 squared plus 1 plus 8. That's definitely even. All right, that'll be 10. If I try 2, I get 2 squared, which is 4, plus 2 plus 8. That's definitely even. If I try 3, let's see, that's a 9 plus 3. That adds up to be 12 plus 8. I also get even again. In my opinion, I believe this is going to be a true statement. Okay, now when I'm trying to prove this here, it just says let n be an integer, and I don't have a definition to really rely on that kind of gets me to the next step. Like if it said n was even, I would know exactly what to do now, because I could just plug in definition of even, and like the previous example. Same if n was odd, I would know exactly what to do, but it just says integer. So there's not a whole lot of guidance there. In fact, we tested both even and odd integers, so I have an idea. Let's prove it first if n was even, and then let's prove it again assuming that n was odd. And that should cover all cases. And cases is the word that we want to say here. We actually are going to prove this through cases. I'm going to say case 1. Let's let n be even. Now the idea of cases is that we're subdividing our hypothesis into categories, but we have to make sure that we include every possibility. In this case, even odd. Those are the only possibilities. And then we're going to show that our result is true for all possibilities of our hypothesis. And so our cases are kind of splitting up the work into easier little sub-packets, if you want. Okay, so we're going to let n be even. Then at this point, it's just pretty much just like the previous examples. N is 2k, where k is an integer. So n squared plus n plus 8 is the same thing as 2k squared plus 2k plus 8. Square the 2k, get 4k squared. And then so I can factor out a 2 out of everything. And I can see then that I have n squared plus n plus 8 is 2 times an integer. We'll say 2 times j, where j equals that expression. So if n was even, we definitely know that n squared plus n plus 8 is even. Let's do the odd case now. So case 2, we're going to let n be odd. Then by definition, n is 2k plus 1, where k is some integer. And hopefully this is starting to feel just a little formulaic by this time. If not, just keep practicing, because that's where you just got to get the experience. If you haven't done this before, it can be very strange. But we know n squared plus n plus 8 is the same thing as 2k plus 1 squared plus 2k plus 1 plus 8. And we got to do some foiling again. We get 4k squared plus 4k plus 1 plus 2k plus 1 plus 8. And hopefully that ends up being even. I think it does, because I get 4k squared plus 4k. Actually, we could combine some like terms now, right? We get 6k, and then we have 2 plus 1s and an 8, so let's go plus 10. That's even because I can factor out a 2 out of everything. 2k squared plus 3k plus 5. Okay, so we can say by case 1 and 2, if n's an integer, it doesn't matter if it's even or odd, n squared plus n plus 8 is definitely even. End of proof. We did it. Awesome. So let me point out one thing here. I've had students in the past do something like this. They'll get to like right here, and then they'll say sum of evens is even. Now that logic is very sound. If you have proven already that two even integers add up to be even, then you are allowed to, I said previous results, that is a previous result. So at this point you could say the sum of evens is even, so we're done with that case. Similarly here, you get to that point, 4k squared plus 6k plus 10, the sum of evens is even. Or even, the sum of two odds is odd, and then, the sum of two odds is even, and then that even plus 8 is also even. Okay, so these are, you can use previous results. However, I think for early on getting started, you need to make sure that you can use the definitions well. So I would start off writing them like we did here, and then once you get a little bit more familiarity with it, you get a little more confidence with it, then we can do things a little bit more exotic, like saying the sum of two evens is even, and so we're going to just skip some steps using that. Direct proof. It's our first case of proof writing. Again, you gotta know your definitions. Hopefully even and odd integers make sense to you. If you have questions in this, I'd be happy to help. You can do it. Just keep working on it. Thanks for tuning in, and see you next time.